When I was in primary 4, yeah, primary 4, although some persons call it basic 4 these days, I don't even know which is right anyway, but in my days it was primary 4. My teacher, Mrs. Bridget, did an experiment in class, or should I say magic. She took a piece of paper, took a pen, rubbed the pen against her head vigorously, then brought close to the piece of paper and it attracted the paper. Back in the day, that was a big deal. That was a big deal. How can a piece of paper be attracted to a pen? It was surprising. My friends and I were blown away. So she was explaining and she made mention of something called charges. I did not really care about charges. What I cared about was the experiment. I wanted to replicate the experiment to do the same thing for myself and get to know how these things work. All right. So after some time, I did the experiment and it worked. So I'm going to try and do the experiment now. I'm going to explain to you why these things work. Let's try and do the experiment. Now this is the piece of paper right in my palm and this is the pen. So let's try and do the experiment. It's not so easy. It worked. Now the reason why the experiment worked was because of these tiny things called charges. Mrs. Bridget explained to us back then that it was charges, and fast 4 years later I now know for certain that it happened because of charges. Now to explain charges, we must talk about an atom. In fact, it all revolves about an atom. Now atoms have protons, atoms have electrons. Protons are positively charged while electrons are negatively charged. They're the negative charges you have in an atom. Now ideally, an atom is electrically neutral. That means that the number of protons and the number of electrons are equal. Because they are equal, the positivity tends to cancel out the negativity. So an atom is supposed to be electrically neutral. However, in some cases, in some atoms, they can become positive charge or can become negative charge, right? So if, for example, let's look at sodium. Sodium, for example, is electrically neutral. It has 11 protons, it has 11 electrons. In some cases, sodium can lose electron because it tends to be electropositive. When sodium do that and loses electron, the number of protons become more than the number of electron. Electron was 11 before, it decreases to 10. Protons still remain 11. So because you have 11 protons and 10 electrons, proton more than electron, therefore sodium is now a positive charge. Alright? The same thing happens for other elements. Potassium, calcium, francium, and the rest of them. Even chlorine, the same thing. Chlorine has 17 protons, 17 electrons. So during chemical reaction, chlorine tends to accept electron because it's electronegative. When it accepts electron, the electron number changes from 17 to 18. Proton is still 17, but electron is now 18. That means electron is now more than proton, a difference of 1, right? Therefore, chlorine becomes a negative charge. So let's wrap this up. What I'm saying in a nutshell is that a proton is a positive charge. An atom can be a positive charge when it has more proton than electron. The same way, an electron is a negative charge. An atom can be a negative charge when it has more electrons than protons. All right. So this idea of charges was the reason why the experiment worked, and the reason of what I'm going to discuss today: charges, electric field. Now, for electric field, we'll start by talking about field. What is a field? Now, to explain field and to explain charges again, I will explain by using, let's say you're in the kitchen and you're trying to prepare. Let me just generalize. Trying to prepare noodles, right? Now, when you put the noodles in the pot, you add water, put whatever. I don't care. You prepare yours, but you're trying to prepare noodles now. You notice that the aroma of the noodles is not just within the kitchen. Someone in the sitting room can, perceive what you're doing, can perceive the aroma. Someone outside can perceive the aroma, right? Probably the neighbor next door. Everybody around can perceive, or let me not say everybody around. Let's say those persons around you can perceive the noodles, right? Like you're preparing something good. And sometimes some of them just, come to you, say hello, just to, you know what I mean, right? Now, the noodle, the pot of noodle now is a charge. Why the region where this pot of noodle can influence, the area where this pot can influence, can draw attention from, is now called the field. It's the same thing as when you describe this stuff using a pot of stew. You're preparing stew and the aroma comes out, people perceive the aroma and they know what you are doing even though you're not in the kitchen with you. So that region where the aroma covers is the feed, while the pot of stew now is the charge. So a feed, therefore, is a region or space where a force can be felt or where a force can be experienced. That's how I define feed in physics. So the same way you have it for pot of stew, you have it for noodles, you also have the same thing in the case of electricity. So a charge has a field around it, has a region around it, where we call, or which we call electric field. Because charges are electric in nature, they can be positive, they can be negative. Therefore, the region around the charge is called an electric field. Now, many years ago, a French guy called Charles Augustin de Coulomb in the year 1785 told us about a force that exists between charges. He said, if you bring two charges together, let's say these are the charges, for example, you bring these charges together, he said there's a force of attraction between these charges. And the force depends on the magnitude of the charges and also depend on their distance apart. He said that if you have this as a charge, have this as a charge, and they are brought closer, he said the force will increase between them. If they are placed far apart, the force will reduce. He also said that if this charge is bigger than this charge, let's say you have a big charge here, you have a big charge here, they are very, very big, the force increases. If they are very, very small, the force decreases. That means that the value of the charge depends on the size of the charge and also depends on the distance between the charges. So, in better terms, see what he said. Charles Coulomb said that the force of attraction or repulsion between two objects is directly proportional to the product of their charges and inversely proportional to the square of their distance apart. Let's put that into writing. That means that force is directly proportional to charges. Now we tend to use Q1 and Q2 as the symbol of charges, while F is force. So he said F is direct to Q1, Q2, right? He also said that F is inverse to 1 over R squared. That means that as the magnitude of the charges increases, the force also increases. As the distance decreases, the force increases. This is inverse relationship. In inverse relationship, an increase in one variable leads to a decrease in the other, or an increase in this variable leads to a decrease in this variable. Now, when we merge these formulas together, or rather these expressions together, we can now see FF. F, this represents the symbol of proportionality. I'll come here, I'll do this. Q1, Q2 over R squared. All right, this is not a formula, it's a mathematical expression of what Coulomb told us. If you're going to change this now to an equation, we'll come out and say F therefore is equal to KQ1 Q2 over R squared. This right here, the formula that was given to us by Coulomb, where of course Q1 is the first charge, Q2 is the second charge, R is distance apart. Please note something, in this topic, we do not represent distance by using D, we represent distance by using R. R represents distance apart, F represents force, and K is the constant. Now, K has its own formula, 4 pi E naught. That's 1 over 4 pi E naught. Apart from having its own formula, K also have its value, a constant value. The value for K is given as 9 times 10 raised to power 9 Newton meter square per Coulomb square. This is the value for K. And of course, this is the formula for K as well, where E naught is permittivity of free space, and the value for E naught is given as 8.85 times 10 minus 12 farad per meter. All right, so if I place this value now, 8.85 exponential minus 12 fm minus 1, I place this value here. Of course, no pi is a constant, 3.142 or 10 over 7, right? 1 over 4 times 3.142 times this value now will give us 9 exponential 9. That was how this value was got, 9 exponential 9, right? So if you're asked the question, what's the force of attraction between two charges whose values are 2 Coulomb and 3 Coulomb, and the distance between them is 2 meters? To solve that, you use this formula, F equal to KQ1 Q2 over R squared. F is what you're looking for. K is a constant, 9 exponential 9. Q1, 2 Coulomb, Q2, 3 Coulomb, and distance, you place the value there. Remember that this distance always have square. You place the value there, you solve, and you have your answer. All right. Now, that said, you should know that not all the time you solve this way. There are times where they will give you questions in exam. They can tell you if the force between two charges, Q1 and Q2, if the force is 3 Newton and the distance is 2 meters, what will be the force if the distance is 3 meters? In this case, they didn't give you the value of the first charge. They didn't give the value of the second charge. So you're not to solve with the charges. This is a question that simply involves force and distance, force and distance. From what we have here, that means I'm not going to solve with F proportional to Q1, Q2. We'll solve with F proportional to 1 over R squared because it involves just the force and distance. So I'm going to work with this. I'll come out and say F is direct to 1 over R squared, right? That means F is equal to K over R squared, right? That means if I make this K to the formula now, K is equal to F R squared. F1 R1 squared is equal to F2 R2 squared. This is the formula I am going to use to solve in this case that involves just force and distance. All right, it will involve force, distance, charge. We solve with this formula. Force and distance only, we solve with this formula. This was what Charles Coulomb told us about back in the day. Please note something, that this explanation is very important. All right, and electrostatic is very important in physics. This whole stuff is the basis of electrostatics. Coulomb's law is the reason why you tend to have lightning. All right, it's very important. Now the next part is electric field intensity. Now it is called electric field intensity or electric field strength or just electric field. Three names that mean the same thing: electric field strength, electric field intensity, or just electric field. Now let's explain this to you so you understand better. Now imagine that we have three charges. Let's say this is the first charge. Let's call this A, right? Let's call this B, and let's call this C. All right, now this charge has its field, this charge has its field, and this charge A has its field. Let's assume these are the charges and these are their fields. Now I have a question for you. Which of these charges do you think we have more force of attraction? Let's assume that we can only talk about force of attraction in this case. We know from Coulomb's law, it said that the force of attraction or repulsion between two objects is directly proportional to the product of their charges and inversely proportional to the square of their distance apart. So in this case, let's assume that the charges are of different polarity. So let's say this is a positive charge, this is a positive charge, negative charge, negative charge. So in this case, you have attraction, right? In this case, also attraction. So between the first case, this is the first case, this is first case, and this is the second case between these guys. So first case between these guys, A and C. Second case between A and B. In which case do you think there will be more force of attraction? Will it be A or will it be B? Assuming B and C have the same magnitude, will it be AC or will it be AB? All right. I don't know what you're thinking. I don't know what you said. I don't know what you have in mind. But the force between A and C will be more than the force between A and B. Why is that so? From Coulomb's law, right? Coulomb said that the force of attraction is directly proportional to their charges and inversely proportional to the square of their distance apart. That means if the distance is small, the force becomes more. If distance is more, the force becomes small. So based on this now, it is very, very clear that the force here will be more than the force here, right? And check this out. C is in the field of A. B is in the field of A as well, right? That means that this region now, this region should have more strength in pulling charges towards it than this region. So that means that the farther apart you are from this charge now, the less the force with which this charge will pull it towards itself, or the less the force with which this charge will pull other charges towards itself. That means that if you have a charge outside, let's say you have a charge here, let's say this is charge D, for example, there's every tendency that this charge might not be able to pull this charge in because this charge is not in its electric field. This charge is far away. Therefore, the strength or intensity with which A will pull D will be very, very small, it will be minimal, it will be almost redundant. Whereas in this case, it will pull this guy to itself now with maximum effort or maximum force. So that means that electric field intensity is the force used in pulling a unit charge to itself. So when you hear the word electric field intensity and you're asked, what is it? You say, okay, this is defined as the force exerted on a unit charge. From what I've said, now I can come around and say electric field intensity is force per charge. The symbol of force is F. I'm sure you're aware of that. The symbol for charge is Q. So if E is force over charge, which is F over Q, we can therefore say E is equal to F over Q. If you are asked the unit for this, force is in Newton, charge is a Coulomb, right? That become NC minus 1 as the unit for electric field intensity. It can be called electric field intensity, electric field strength, or just electric field. Recall, now we're trying to get to that formula from this now. Recall that F is equal to KQ1 Q2 over R square, right? If F is equal to what you have on the board, can we replace this stuff? Can we replace this F and place this guy here? Of course we can. When we do that, this becomes E equal to KQ1 Q2 over R square, right? All over Q. All over Q. In mathematics, you can change this now to say E is equal to KQ1 Q2 over R square over Q can be presented as divided by Q, right? And divided by Q is like saying times 1 over Q. When Q cancel out 1Q from what you have here, E therefore is equal to KQ over R square. That means that electric field intensity or electric field strength has two formulas. It can be given as E equal to F over Q, can be given as E equal to KQ over R square. The next part now is electric potential. Now let's explain electric potential in very simple thing that you understand. Now imagine this to be a charge. Imagine this to be a charge. Let's assume this is charge A. This is also charge A. In fact, the charge that is here is the same charge that I moved and brought to this point now. So they are pretty much the same charges. Let's say it's positively charged. Alright. And let's assume you have another charge here. Let's say this is charge B and it's negative. And that charge is, let's say at this point, this is charge B and it's negative, right? Obviously, we know already from what Coulomb said that there will be a force of attraction between these guys. And that force of attraction between these guys, right? So this guy will pull this guy towards itself. This will pull this guy towards itself, right? Now, if you watch the video on work, energy, and power, I don't know if you've seen the video. If you've not, just subscribe to this channel and watch the video on work where I explain it in very simple terms. I explain work in very simple terms. Work is done whenever a force is applied on an object and the object moves a distance in direction of such force. That means if A pulls B, A automatically have done work. Why? There was force involved, which is electric force, right? Which can be got by using the formula KQ1 Q2 over R square. I know K is a constant, right? I know Q1 might be this and Q2 might be this. If I put 9 exponential 9 here, Q1 is this, Q2 is what you have here, R is distance between them. I'll be able to get the force with which this guy will pull this guy to itself. If the force, for example, is 10 Newton and distance from here to here is 4, 10 times 4, answer is 40. That means the work done in moving B from this point to A now is 40 joules. That's the electric work done. In this case, distance, if as we assume that in this case distance is 4, we can assume in this case distance will be less than 4, right? We can say 2 meters. So if here you have 4 meters and here you have 2 meters, obviously, in which case do you think you do more work? Yeah, right? Exactly. So when someone asks you what is electric potential, it is the work done in moving a unit charge from one point in electric field to another. The work done in moving a unit charge from one point in an electric field to another is called the electric potential. And mathematically, it is given as V equal to work done per charge. Recall that, we said it before, that work is force times displacement, right? If work is force times displacement from work, energy, and power, and in this topic, we always represent displacement using arrow. We can therefore say work is F times arrow, right? If work is F times arrow, can we now say V is F times arrow over Q? Yes. There again, recall that F is equal to KQ1 Q2 over R square. You know we said this before. That's why I started the topic from Coulomb'S law. We said F is KQ1 Q2 over R square. So if F is KQ1 Q2 over R square, we can remove F here and substitute. In that case, we come here and say V is equal to, let me wipe up this part. In that case, we come out and say V is equal to, in place of F now, I'll say KQ1 Q2 over R square, that's in place of F, times R. I'll come here and say times R all over Q over Q, right? Now, over Q means divided by Q, which also represents times 1 over Q. So I'll come out and say V is equal to KQ1 Q2 over R square times R over Q now means times 1 over Q, right? Now, if I'm to multiply the numerators and multiply the denominators, of course, you know this should have a visible 1. I can simply just cancel out, but some persons, they might not understand what I'm doing. So I'll just, multiply everything. I'll come around and say V is equal to KQ1 Q2 times R, numerators, right? Over R square times Q, denominators, right? I mean, R square times 1 times Q is R square times Q. Q cancel out 1 Q. R cancel out 1 R. Therefore, V is equal to KQ over R as the second formula for electric potential. So this is the first formula for electric potential, and this is the second formula for electric potential. It's very, very important. The next part now will be the relationship between electric field intensity and electric potential. Okay, for the relationship between E and V, see what you are going to do. Recall that E is KQ over R square, right? I'm sure you remember this. And we said V is KQ over R. If E is KQ over R square, we can say E is KQ over R times 1 over R, right? If KQ over R is KQ over R, which is V, we can then substitute V for KQ over R to now say E is equal to V times 1 over R. That means E is V over R. That means V is equal to E R. This right here is the formula relationship for electric potential and electric field intensity. A quick one. Let's give a quick review or a quick recap of all the formulas we've established today. There is F equal to KQ1 Q2 over R squared. This was the first formula we gave today. We then said that K is 1 over 4 pi A naught. Do not forget. We said for questions involving just force and distance, F1R1 square is equal to F2R2 square. After this, we talk about electric field intensity, also called electric field strength or electric field, where we said it is force per charge, or it is given as E equal to KQ over R square. We then talk about electric potential, where we said V is work done per charge, or V is KQ over R. And of course, the relationship given as V equal to E R. These are the things we've talked about today. Now, it's simple to know the formula for electric field intensity and formula for electric potential. Think of it this way. First of all, understand that for electric field, okay, not here, the other part, just you can go back and check what we wrote. We said electric field intensity, right? Now, for electric field intensity, you know something. The symbol is E. We indicated before now that the symbol is E, right? So whenever you're asked for electric field intensity and you do not know the formula, just know that first of all, electric field intensity and electric potential always talk about charge. They always have charge as the denominators. Observe F over Q, observe W over Q. There's always Q as denominator. Now, in the case of electric field intensity, because in the ABCD alphabet series, after A, B, C, D, E, after E, what you get next is F. That means for formulas that involve electric field intensity, whose symbol is E, the formula becomes E equal to F over Q. So this is simple to always remember. If I ask you tomorrow, what's the formula? Let's say you're asking an exam. What's the formula for electric field intensity? Of course, you should know the symbol. It is E, right? After letter E, what else do you see? Letter F. So F over Q, that's the formula. You get the point. Now for electric potential, which you can so go back and check, we said the symbol for electric potential is V. For electric potential, which is V, still working on the alphabet series. If you read the alphabet series, M, N, O, P, Q, R, S, T, U, V, W. After V is W. So in this case, you come out and say, oh, after V, which is symbol for electric potential, it is W over Q. And that's simple to know the formula for electric potential. All right. So that's it. This is all you need to know about the topic. One last thing you need to know that they don't often ask in exam, but just know, is that you see this stuff we call electric permittivity of free space. There's a formula called relative permittivity, or there's something called relative permittivity, and it's given us permittivity of medium over permittivity of free space. Just add this to the formulas. So now we have 1, 2, 3, 4, 5, 6, 7, 8, and of course 9. So that is it about this topic. Now we're going to solve questions based on what you've said to see how much of these things you really know. So this is the first question. The force of repulsion between two negative charges, 4 Coulomb and 5 Coulomb, separated by a distance of 2 meters is. Now if you notice this question, if you observe, they did not give you the value of the constant. They didn't tell you k is equal to 9 exponential 9. But you should know that k is always equal to 9 exponential 9. They asked for the force. That means you need to look for F, right? They gave you charges. The charges they gave to you were 4 Coulomb and 5 Coulomb. That means Q1 we can assume is 4 Coulomb and Q2 can assume is what now? 5 Coulomb. While distance between them is 2 meters. Which formula do you think we have to apply in solving this question? You ask yourself, of all the formulas we give, which formula of all the formulas we give involve two charges? There's only one formula that involves two charges, which is the first formula as given by Coulomb. So we can come right and say from F equal to KQ1 Q2 over R square, we can say F is equal to, what is K? Is a constant, right? 9 exponential 9. What is Q1? That's 4. What is Q2? That is 5. What about R? R is 2. But because it is R square, that becomes 2 square. And of course, 2 square is like saying 2 times 2. 2 times 2 is 4. So if this is 4, 4 can cancel out 4. F equal to, if 4 cancel out 4, you now have 5 times what you have here. What is 5 times 9? 45, right? So that becomes 45 times 10 raised to power 9. Or 4.5 times 10 raised to power 10 Newton. This becomes your answer. If, however, solving this way is obfuscating for you or it's confusing, you don't have to solve and get the answer this way. You can just say F is equal to 9 times 10 raised to power 9 times 4 times 5 over 4. Of course, you know this 4 now is coming from 2 raised to power 2. What is 4 times 5? 20. 20 times 9. What do you get from there? 180. So you come out and say F equal to 180 times 10 raised to power 9 over 4, right? Can 4 go into 180? That's the next question. You start by asking yourself, can 4 go into 80? Yes, 4 can go into 80. 4 into 80 is what? 20. What about 4 into 100? What do you get from that now? You get the point now. 4 into 100 is what? 25. What is 25 plus 20? 45. So answer become 45 times 10 raised to power 9 or 4.5 times 10 raised to power 10 Newton. This is your answer. You either pick this or you pick this. That is how it is solved. Let's have another question. Now here is the second question. How do we solve this? Find the work done. We come around and say W equal to unknown. In moving 2 Coulomb charge, that means Q is equal to 2C. Between 2 points S and Y. In an electric field, if the potential difference is 100 volts, so V is 100 V. So they ask us in this case to look for the work done. So from what we've discussed before, which formula involve W, Q, and V? You know the formula, right? The formula says that V is equal to work done over charge. So if I input these values into the formula, that means that we can come and say 100 is equal to, what is W? Unknown. What is Q? 2, right? So work done is equal to what you cross multiply. Become equal to 100 times 200 joules. Alright, so that is it. It's not really difficult. All you have to do is just watch the video carefully, understand the formulas. If possible, you can jot out or write out the formulas that can help you in the examination. Alright, that is all about electric field. Now, back to what I said initially, Mrs. Bridget. We now know that the reason why the pen was able to attract the piece of paper is because of electrostatic force, because of the field generated when I rub the pen on my hair. There will be electron loss. As a result, in bringing the pen close to the paper, it tries to attract the electron on the paper. By so doing, it attracts the paper, in totality. Now, when you try this experiment with a large paper, it will not work because the electrostatic force is not enough to lift the paper off my palm. But when you try this experiment with little paper, in fact, that's the reason why we use small piece of paper. It becomes easy for the piece of paper to be attracted to the pen. You can check my short session on short videos on this. Check the session and observe other questions I've solved. Alright, that is it. My name is Dr. Olotu and I'm here to help you fix jam before jam fix you.